Good afternoon. I'm going to talk about joint work with Anupam Datta and Yair Zik about how to explain the behavior of learning systems. So learning systems today are everywhere, and they're used for things from credit decisions to law enforcement. And a lot of these applications can have significant impact on people's lives. On the other hand, these systems can be extremely opaque. For example, consider this average Joe here who uploads all his user data to this shiny big data credit classifier and gets rejected. And once he gets rejected, he has no idea why he got rejected. And even if you give him the source code for the classifier, that does not suffice as an explanation for why he got rejected. Consider a different situation where a large group of people apply for a loan, and you find that a lot of the men get accepted, but very few of the women do. And these kinds of behaviors of these systems can be extremely difficult to explain. So the impact some of these systems can have on people's lives, combined with how opaque these systems are, has led to the birth of this new research area called Algorithmic Transparency, where there is a great need for tools and theories to explain the behavior of decision-making systems. And the main motivation for providing transparency is that explanations help in diagnosing harms that arise from inappropriate information use. And some examples of these harms are integrity harms, where you want to know if incorrect data was influential in, say, a credit denial. Or for privacy, you want to know if things like health status or a proxy of health status was influential in targeted advertising. Similarly, for fairness, you want to know if race, gender, or proxies of these are influential in something like job targeting. So in this space, the particular problem we're looking at is that of input attribution, which asks the question of how much influence do various inputs or features have on the classifier's decision about individuals or groups. And to give you an example of the kinds of explanations we can give, so consider Joe who has this profile. The kinds of explanations we can give is saying that the reason he was denied is because he's a fisherman and he has very low education. He also has high capital gains, which would have led to positive outcomes if these other negative factors weren't present. So for the rest of this talk, I'll explain how we come up with these explanations. So the main challenge in identifying influence of different inputs is that inputs can be correlated. Consider this classifier here, which takes in as input age and income, and the only input it actually just uses is income. However, because age is correlated with income, for example, a poor grad student like me in his 20s will make a lot less than a full professor in his 50s, hopefully. And because these inputs are correlated, the decisions of these outcomes are also correlated with age and income, even though only income is being used. A second challenge is that we want to answer a general class of transparency queries, depending on who's asking. So for example, an individual might be interested in which input had the most influence on my credit denial. I don't care about anyone else. Or an auditor might want to ask which inputs have the most influence on the credit decisions of women on average, or or this more nuanced question, which is what inputs influence men getting more positive outcomes than women? So to solve this, so to answer these kinds of questions, we have developed a family of metrics called Quantitative Input Influence, which allows us to measure the influence of an input of a system on its output. And I'll explain the three key ideas that go into this definition. The first one is that we use a causal intervention that allows us to deal with correlated inputs. Our definition is parametric in a quantity of interest, which lets us support a general class of transparency queries. And finally, and this is a cool insight, that that influence can be viewed as a cooperative game, which allows us to compute joint and marginal influence. And this is what I'll explain for the rest of this talk. So informally, the quantitative input influence of an input on a quantity of interest is the difference in the quantity of interest when the input is replaced with a random value via an intervention. So the two things we need to explain here are an intervention and a quantity of interest. So let's look at what interventions do. So going back to Joe's classification example, if we want to figure out if age had any influence on the decision or not, what we do is keep his income fixed and replace his age with random values from the population. We see that the outcome does not change at all. On the other hand, when we keep his age fixed and replace his income with random values from the population, his outcome changes for a lot of these inputs. So this is the general strategy we want to use, that we have the true distribution of input variables, which is represented by capital X. And we have this intervened distribution where the input we want to study has been replaced with the marginal distribution of that input. When we pass these two distributions through a classifier, we get a distribution over outcomes. And for these distributions, we can be interested in different statistics. So in this example, I am interested in the probability that Joe gets positive classification. I measure this probability in both distributions and compute the difference. That gives me the influence of an input I for Joe's classification. We can generalize these ideas to different statistics of the system. So for example, we can look at the classification outcome of a different individual. We can look at the classification outcome of a group of individuals, or we can look at this statistic which compares the difference between rates of classification for men and women. And once we define this statistic, we apply the same strategy of applying a randomized intervention and computing the difference of these statistics in the original distribution and the intervened distribution. So putting these two pieces together, the quantitative input influence of an input I on a quantity of interest is just the difference in the quantity of interest with or without this random intervention. So what I've explained to you so far is essentially the influence of a single input while keeping the other inputs fixed. But often this is not enough. So to see why, consider this example here, where this new classifier only accepts old and high income individuals. Joe, on the other hand, is young and low income, so changing exactly one feature creates no difference on his decision. So single inputs often have insignificant influence. And the naive solution to this problem is just to expand this idea to sets of inputs, and instead of changing one input, you change multiple inputs together. So that gives us this natural definition of a set QII, where you consider a set of features to be a single feature, and you intervene on them. However, within a set, not all features are equally important. And to measure the influence of a feature within a set, you can just compute a marginal quantity, which, so for example, in this case, this is the difference of the influence of age and income minus the influence of income, which gives you the marginal influence of age in this set of age and income. But age belongs to lots of different sets, and how do you make sense of all of these different differences? And game theory gives us a very elegant solution to this problem. So essentially, the idea is that we view this set QII as a cooperative game, and cooperative games have been used to study lots of different problems with the same structure, such as voting, where changing a single vote in an election makes no difference, but every voter has some influence. So we just use all of that theory where our agents are features, and the value is just the influence of a set of features. And once we make this observation, we can use this very classic result from Lloyd Shapley, which says that for cooperative games, the only aggregation measure over all of these sets which satisfies some very natural properties which hold in our setting is the summation. So I don't want you to focus on the details of this, but notice that this requires a summation over an exponentially large number of sets. But we show in our paper that it's possible to efficiently approximate the sum by randomly sampling sets. So now that I've described the three key pieces of our paper, let me show you some examples of explanations. So to illustrate explanations, we built two test applications for our paper. And I won't be able to show you all the different kinds of explanations, but I'll focus on two. And the two applications we developed are those of, one is a predictive policing application, which uses a national longitudinal survey of youth to predict whether some person is suspicious or not. And the second is an income prediction application, which uses a benchmark census data set to predict whether somebody is high income or low income. So now, and we implemented this with a bunch of standard textbook machine learning algorithms. So let's look at Mr. X, who was denied by the income classifier, and he is a Vietnamese with reasonably high capital gain who immigrated to the US, and he might wonder that his immigrant status is the reason why he was denied. But once we look at the classifier, we learned we can give him an explanation saying that his education status, his marital status being single, and the fact that he is living with his parents is actually the reason why he got denied. And his race or his country had nothing to do with it. So explanations like this can assuage concerns of discrimination. Now let's look at Mr. Y, who's a similar immigrant individual with high capital gain and is a fisherman, the example we saw in the beginning, and he might have similar concerns. So now the reason why he got denied was his education and his occupation of being a fisherman. So the point here is that explanations of superficially similar people can be very different, right? So, apart from the definition, we show that QII measures can be approximated reasonably efficiently. We also show that we can add differential privacy to QII very cheaply to protect the data of the individuals whose data was used to provide these explanations. Yeah. In terms of related work, the randomized causal intervention, which we used in this paper, shows up in a number of places. But these things can be viewed as instances of our more general theory of influence. There has also been a lot of work to use associative measures for transparency to explain the behaviors of machine learning algorithms. But as I argued earlier, correlated inputs can hide causality. And finally, one orthogonal approach to getting interpretability is to get interpretability by design, where you constrain the design of your models to have some intuitively explainable structure. But when you constrain the design of your algorithms, you can have a potential loss in accuracy, which our method avoids by being completely black box in terms of the algorithm you use. So to conclude, as a part of the broader algorithmic transparency question, we provide definitions of input influence. And the key ideas which I want you to take away from this is that you need causal reasoning to figure out which inputs were actually used by a classifier. Being parametric in this abstraction of a quantity of interest can help you give personalized explanations. And finally, game theoretic influence gives you a very elegant solution to the marginal influence question. Thank you. Yeah.
I was looking through the paper, and yeah. I wondered if, in your remarks there at the podium, you could relate this work to security or privacy.
Right. So transparency is about. So my motivation for transparency came from diagnosing inappropriate uses of information, and security and privacy is exactly about preventing inappropriate uses of information. So that's the connection to security and privacy. Yeah.
I'm just going to jump in and add to that both the FTC and the European Union are talking a lot about algorithmic transparency in terms of privacy. That's sort of become a hot topic in the last 9 months, I would say.
So a comment and a question.
Yeah.
Oh, Rob Cunningham, MIT Lincoln Lab. The comment is that I've seen some work similar to this in the area of interpreting neural network decisions that might be fruitful for taking a look at. Mm-hmm. And the question has to do with the amount of time it takes to do the process that you are doing here. If I think about this in geometric space, effectively what you're trying to do is map out in n-dimensional space the dimensions of the decision that's being made.
Right.
If n is larger than just a small number of features, this can take a long time, I think, but maybe not.
Yeah, so that's exactly right. If you have a huge number of features, then computing these measures exactly can take a lot of time. But we show that when you have these very large sums, and each of the terms of those sum are bounded, then by randomly sampling the terms of the sum, you can derive very close approximations of that sum with a constant number of samples, essentially. Thanks. Yeah.
Sorry, again, Pavel Laskov, by Munich. I'll ask another question.
Yeah.
In 2002, Ryan Rifkin from MIT wrote a very insightful, very interesting dissertation, whose its content is not really related to your work, but its title may be very.
Okay.
So this dissertation was called "Everything Old is New Enough."
Okay.
A fresh look at the historical approaches in machine learning. So basically, the gist of this dissertation was to show that a lot of the ideas that were mainstream in the 90s and 2002 actually surfaced in the statistical literature as early as in 1920s. Why is it related to your talk? The fundamental setup of your method very closely reminds me the ideas of Bayesian learning. So you also replace individual samples with their marginals, with probabilities, and try to do reasoning on distributions as opposed to, let's say, individual data. Yeah, so this is a very, very insightful approach. Can you comment on how your approach actually differs from Bayesian learning? So this has been a very established method in machine learning, also extremely successful. What is here old enough?
That's a great question. So we view our work as sort of a generalization of experiment of causal experimentation, where that work has mostly focused on looking at binary choices, where what is the effect of A as compared to B. I'm not aware of the particular Bayesian learning framework you're talking about, so maybe we can talk about that offline and compare approaches.
Well,
yeah. Thanks.
Take out.
Can I just ask one clarifying question? So in order to do this, do you require access to the sort of entire training set of the data?
So you don't need access to the training set, but you need access to a large representative sample from the input space, which can be completely different from the training set, though.
Right. So that works well if you're the company who wants to do this and figure
Right.
out what's going on inside your own algorithms. But it's more difficult if you're an auditor who's trying to assess whether somebody is.
Exactly. So an auditor will need to have some amount of cooperation with the company it's auditing to be able to test these properties. Yeah. Okay.
One more question. Yeah.
Yeah.
Can you hear me? Okay. First of all, relationship to privacy, it's more related to legal regimes. Data protection is about making processing of data transparent. So algorithmic transparency is seen as part of privacy via data protection, which is European law, and I hope that in the US there will be some related laws as well. I wanted to ask about assumptions you made with respect to accuracy of the machine learning applied by, say, the decision-making company. Do you make any assumptions or not? And how does that relate to the model that you have?
Right. So we don't need to make any assumptions about the accuracy of the classifier itself. So the true classification itself is something we don't care about. We're just trying to analyze the model as it is. and the outputs it gives. So the accuracy of the classifier with respect to the true labels doesn't have anything to do with the influence question as such. Yeah.
So what is then your evaluation if the accuracy of the model is very low and you find impact? I mean, you're suggesting there's no relationship, or is it that you're not saying anything about that accuracy and what it might have as an impact on the people whose decisions are now being made with this model?
Right. Yeah. So. So the accuracy of the model has an impact on the people who are being classified, which is independent from the influence of various inputs. Now one thing you could use this for is to compute the influence of different inputs on the accuracy and use that as a quantity of interest, and that gives you the sources of inaccuracy in your classifier. Does that make sense? Okay.